For millennia, the universe has revealed its secrets in slow, deliberate increments. Now, a new enigma emerges from the cosmic tapestry. Initial observations, stemming from a routine sky survey by the Kepler Institute in late 2021, hinted at something unusual. What was first dismissed as background noise or instrument error has since coalesced into a compelling, perplexing object, a nebula unlike any catalogued before. The object, informally designated Aethelred by its discoverers, promises to challenge fundamental assumptions of stellar evolution and cosmic mechanics. To understand the Aethelred, we must first contextualize its existence. Nebulae are vast clouds of gas and dust, the stellar nurseries where stars are born, or the cosmic tombs left behind by dying stars. Historically, their luminous beauty has captivated humanity. Dr. Lena Hansen, an astrophysicist at the European Southern Observatory, explains, nebulae are fundamentally the building blocks and remnants of stars. They tell us about the life cycle of cosmic matter. Their composition, movement, and interactions provide critical data for understanding the universe's grand narrative. Observing such distant and often faint objects poses immense challenges. The Aethelred Nebula is located approximately 15,000 light-years from Earth, obscured by layers of interstellar dust within the Perseus arm of our Milky Way galaxy. Dr. Kenji Tanaka, lead astronomer on the Aethelred project, notes, its faintness and the obscuring dust meant it was easily missed by traditional optical surveys. Multi-wavelength astronomy, combining data from radio, infrared, and X-ray telescopes, became indispensable, allowing researchers to pierce through the cosmic veil and begin to resolve its hidden features. The initial data, primarily from the ESO's Very Large Telescope and NASA's Spitzer Space Telescope, revealed immediate peculiarities. Spectroscopic analysis, which breaks down light into its constituent wavelengths, showed emission lines that did not fully conform to known stellar or nebular compositions. Specifically, researchers at the Kepler Institute identified unusually strong, fluctuating signals in the mid-infrared spectrum. Dr. Tanaka recounts, "We saw signatures that didn't quite fit our models for hydrogen, helium, or even heavier elements typical of nebulae. It was like hearing an unfamiliar instrument in a symphony." The most striking anomaly, however, was not simply the unique spectral signature, but its temporal variation. Over several months of observation, data began to suggest a periodic fluctuation in the Aethelred's energy output. Dr. Anya Sharma, a theoretical astrophysicist at the University of Cambridge, articulated the emergent hypothesis. The data indicated a rhythmic, consistent emission, what we began to term a silent pulse. This wasn't the chaotic variability of a young star or the predictable decay of a supernova remnant. It hinted at an underlying, structured phenomenon. As more observatories turned their gaze toward the Aethelred, initial findings were not uniformly consistent. Reports from the Subaru telescope in Hawaii, for example, emphasized different peak frequencies in the observed pulse compared to those recorded by the VLT. Dr. Tanaka acknowledges, these discrepancies were frustrating, but crucial. They forced us to re-evaluate our calibration methods, account for interstellar medium effects, and consider the possibility of multiple emission sources within the nebula itself. The scientific community was divided, some advocating for simpler explanations, others for more exotic ones. To reconcile these disparate observations, a collaborative effort was launched, integrating data from across the electromagnetic spectrum. The Atacama Large Millimeter/Submillimeter Array, ALMA, provided unprecedented detail in radio wavelengths, while the Chandra X-ray Observatory mapped high-energy emissions. This comprehensive approach began to paint a clearer, albeit more complex, picture. Dr. Hansen noted, what looked like a single pulse in infrared became a symphony of overlapping periodicities across different wavelengths. This was not a simple, uniform phenomenon. With refined multi-wavelength data, researchers identified a distinct, heavy elemental signature within the Aethelred Nebula's pulse, tentatively named Element X. This element's unique spectral lines, observed by a team at the Max Planck Institute for Astronomy, have no direct match in existing terrestrial or known cosmic elemental databases. Dr. Armin Richter, head of spectroscopy at Max Planck, states, "The resonance patterns are unlike anything we've seen. It behaves like a super-heavy isotope, but with a stability that defies current nuclear models. It's a true outlier." Further analysis of the periodic energy output clarified the pulse as a non-thermal emission, meaning it's not generated by simple heat or stellar fusion processes. Instead, the consistent energy bursts across various wavelengths suggest a highly organized, coherent mechanism. Dr. Sharma elaborates, "The energy output isn't random, it has a structure, a signature, almost like a coded signal repeating at precise intervals. Its power output, while periodic, varies subtly, hinting at complex internal dynamics rather than a simple on-off switch." One leading hypothesis posits that the Aethelred Nebula represents an entirely new, exotic phase of stellar evolution. Perhaps an ultramassive star collapsed into a novel type of pulsator, or a binary system undergoing extreme gravitational interaction. Dr. Eris Thorne from the University of Tokyo suggests, "We might be observing a magnetar interacting with a very compact, superdense companion, creating a complex, periodic energy transfer. The pulse could be the result of relativistic jets or gravitational waves." This theory attempts to explain the observed power and periodicity through known, albeit extreme, astrophysical processes. A more speculative, yet compelling, theory proposes that the Aethelred Nebula's pulse is a manifestation of dark matter interaction. Some physicists suggest that the nebula might be nestled within a localized concentration of dark matter, and its periodic emissions could be a byproduct of exotic dark matter decay or annihilation. Dr. Elise Moreau, a particle astrophysicist at CERN, states, "If we are seeing the direct energy signature of dark matter decay, perhaps mediated by element X, it would be a paradigm shift." However, direct evidence of such interaction remains elusive. This theory remains highly debated. To further differentiate between these competing theories, state-of-the-art instruments were brought to bear. The recently commissioned Extremely Large Telescope, ELT, provided unprecedented spatial resolution, allowing astronomers to scrutinize the Aethelred's internal structure with greater clarity. Simultaneously, advanced interferometry techniques were employed to precisely map the source of the pulse. Dr. Tanaka remarks, "We needed to see if the emission originated from a point source, a diffuse region, or a complex, distributed network within the nebula. The ELT was our eyes." The combined data from the ELT and next-generation interferometers yielded a definitive breakthrough. The silent pulse was confirmed to originate from a distinct, compact region within the nebula's core, rather than being a diffuse phenomenon. Crucially, the periodicity was precisely measured, a repeating cycle of 1.27 seconds. Dr. Hansen's team corroborated this using independent gravitational wave detectors, detecting faint, rhythmic ripples coinciding with the electromagnetic pulse. This consistent, sub-second periodicity points to a highly stable, extremely dense object at the nebula's heart, she affirmed. With the pulse source located, ELT imaging began to reveal the nebula's intricate internal architecture. The Aethelred appears to house a central, highly active region, surrounded by complex, stratified layers of gas and dust. These layers seem to be interacting with the pulsed emissions, resonating at specific frequencies. "It's not a simple cloud, it's a dynamic system," says Dr. Tanaka. The internal structures suggest energy transfer mechanisms that are incredibly efficient, perhaps even channeling the pulse outward in specific directions, explaining some of our earlier observational discrepancies. Further spectrographic analysis, now targeting specific regions identified by the ELT, uncovered a surprising array of complex organic molecules within the nebula, particularly concentrated near the pulsing core. These molecules, previously considered rare in such energetic environments, include long-chain hydrocarbons and various amino acid precursors. Dr. Hansen cautiously notes, while not direct evidence of life, the sheer molecular complexity in an environment with a stable energy source, albeit an exotic one, is certainly noteworthy and pushes the boundaries of astrochemistry. The confluence of new data has led to a refinement, and in some cases, a rejection, of earlier theories. The magnetar interaction hypothesis now struggles to fully explain the element X signature and the complex molecular chemistry. However, elements of the dark matter interaction theory gain new traction, particularly models involving dark photons or other weakly interacting massive particles. Dr. Sharma postulates, we may be witnessing a completely new class of astrophysical object, a pulsating dark matter interaction nebula, where a conventional stellar remnant acts as a catalyst for dark matter decay, driving the pulse. The implications of the Aethelred Nebula silent pulse are profound. If the dark matter interaction hypothesis proves correct, it offers the first direct observational evidence of specific dark matter decay processes, fundamentally altering our understanding of the universe's most mysterious constituent. Even if an exotic stellar mechanism is ultimately confirmed, it would represent a significant expansion of our knowledge of extreme astrophysical phenomena. Either way, Dr. Tanaka states, the Aethelred is rewriting chapters in our textbooks, forcing us to consider entirely new physics. Behind every scientific breakthrough is a human story of collaboration, dedication, and sometimes, intense intellectual rivalry. The Aethelred project exemplifies this, drawing together hundreds of scientists across continents, yet also witnessing passionate debates over interpretations and methodologies. Dr. Hansen reflects, science thrives on skepticism and rigorous challenge. The disagreements, the re-examinations, that's where the truth often lies. It's a testament to the collective human drive to understand our place in the cosmos. Despite remarkable progress, the Aethelred Nebula retains much of its mystique. Critical questions remain: what is the precise nature of element X? Are there similar pulsating nebulae hidden elsewhere? And perhaps most profoundly, what implications does this discovery hold for the potential for life in extreme cosmic environments? Future missions, including planned next-generation space telescopes and dedicated probes, are already being conceptualized to delve deeper into the Aethelred silent pulse, promising even more astonishing revelations. The Aethelred Nebula continues its rhythmic, silent pulse across 15,000 light-years of space, a cosmic beacon challenging our established models. What began as a faint, anomalous signal has evolved into one of the most compelling astrophysical mysteries of our time. It underscores a fundamental truth: the universe is vast, and our current understanding is but a fleeting glimpse into its boundless complexity. As telescopes continue to gaze, and scientists continue to probe, the silent pulse of the Aethelred Nebula reminds us that the cosmos still holds wonders beyond our wildest imaginations, waiting to be deciphered.